How's it going, everyone? Mr. Geyser here with the first video in our Lesson 10b series, where we're still looking at the inverses of exponential functions, but we want to start playing around and manipulating these functions here. Where, in this first part here, the logarithm base b of a positive number x is defined as log base b of x equals y, if and only if b raised to the power of y equals x, by definition. You can read log base b of x as log base b of x. In other words, the logarithm y is the exponent in which b must be raised to get x. A logarithmic function is the inverse of an exponential function, as we discovered in our 10a series. A logarithm that uses base 10 is known as the common log. A logarithm that uses base e is known as the natural log. You can write log base 10x as log and log base e of x as ln of x. A logarithmic scale is any scale that uses a logarithm as a quantity instead of a quantity in itself. We will now look towards graphing logarithm functions and transformations. We want to try and take a look at these 6 manipulations and characteristics of logarithmic functions. We want to start off with that parent function here of that y equals log base b of x. If we happen to have a vertical dilation, that means that some a value is in the very front of our log function here, multiplying it by something. Now, this vertical dilation can also cause a reflection in the x-axis. If this a value happens to be negative in some way, then it reflects it about that x-axis. If we want to reflect it about the y-axis, then there has to be some c value in the front of x, where c is usually equal to -1, where if c is negative, it reflects it about the y-axis. Transformations are still exactly the same. That h value there still affects our x value in an inverse relationship, where h translates horizontally and k on the outside of the function translates vertically. Exact same thing as our exponents, as our parabolic functions, our quadratic, our cubic, all of that jazz. If we combine it all together, we get some y value equals, let me move all that, y equals a times log base b of cx minus h plus k. Easy. Let's put it into practice. Now, let's take a look at example 7. For example 7, we're transforming these logarithmic graphs. We're in example 7, we want to describe how to transform the graph of f of x, which equals the natural log of x, and g of x, which equals the common log of x, into the graph that's given for the function. And we want to write some rule for that x-y pair. In part A, we're given h of x, which equals 3 plus log of x. Now, in general, for this rule here, we're really taking a look at this x and y of g of x is being transformed into x comma y plus 3, where the transformation described here is a vertical translation of 3 units up. For example, you don't always need to use this as an example, but it's nice to have. Example here is that 1 comma 0 for this graph here would move over to 1 comma 3, where it's just moved up those 3 units. Let's take a look at B. For f of x is equal to -2 ln, natural log, of x minus 3, where we can write this rule here that describes that our x and y for our f of x, that original function there, is being moved to x plus 3 minus 2y. Now, where's that plus 3 coming from? Well, remember, our h values are reversed. So when we write that transformation here, what we're really saying is it's a reflection about the x-axis, a vertical dilation of a factor of 2, and a horizontal translation of 3 units to the right. And I want to break down these components here where the reflection about the x-axis is coming from the negative of the 2 that's in front of our natural log. That vertical dilation of a factor of 2 is coming from the actual 2 in front of that natural log. And the horizontal translation of 3 units to the right is coming from that -3 inside of our natural log, which is really transforming our x values plus 3 when we regraph them. As a general example for this here, we can take a look at that example of 1, 0 again, whenever it moves to 4, 0. Let's take a final look at part C. For part C, y equals log base 3 of 2 minus x, where for this rule, we actually get this x and y pair equals negative x plus 2 of y, where I want to try and showcase that we can rewrite this 2 minus x as minus x plus 2. Now, when we want to try and pull out that negative from that x there, that c value that's affecting that x, what happens is we get this negative 1 pulled from both of these terms inside of our log here. That's where that plus 2 comes from, because h is opposite. It comes from that negative 3, or sorry, that negative 2, in the same way that the negative 3 in our example before turned into a positive 3. This is going to be a tricky step for some students, but don't let it fool you. All you're doing is you're pulling out a c value from every term inside of the parentheses of the log. Now for example C though, we do have what's called a change in base. So when we describe this transformation here, it is a change in base to 3 from 10, a reflection about the y-axis, and a horizontal translation of 2 units to the right. I want to break it down just a little bit more, where that change in base there, pretty self-explanatory. You're just describing that we're going from a change in base of 10, or common log, to 3. You're just saying it outright. Then we're describing that the reflection about the y-axis is really coming from the fact that we have that negative being pulled out of that x value there. Finally, that horizontal translation is coming from now that plus 2 that came from this minus 2 that was originally here that we pulled out. Thank you very much for joining me for this first video on our Lesson B series, where we learned about how to describe those transformations of logarithmic functions. I look forward to seeing all of you guys in that next video. Take care.